Welcome to our video tutorial on conditional probability. We are going to look at three sample problems in this tutorial. The first is pictured on the screen. We have a coin that is tossed 4 times. We want to know the probability that there are at least 3 heads, given that the first 2 tosses landed on heads. So if we were writing this out, we would want the probability of at least 3 heads, given that the first 2 tosses were heads. So we have heads, heads to start things off. Now, yes, we have a formula for conditional probability, but what we're looking at in this scenario is a problem that's more suited to writing out the sample space. So over here, I'm going to write out the sample space. The sample space in this problem requires that we only need to consider that the first 2 tosses of the 4 landed on heads. Nothing else matters. All we're looking at is what happens when the first 2 tosses land on heads. So we could have heads, 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 tail, heads, heads, tails, heads, and heads, heads, tails, tails. That's it. Nothing else matters. Those are the only outcomes that have the first 2 results being heads. So there are 4 total outcomes that make sense when we know that the first 2 tosses landed on heads. Now, how many satisfy the criteria we want of at least 3 heads? Well, the one that I just highlighted in blue has at least 3 heads. The one also now highlighted in blue has at least 3 heads. And this one also has at least 3 heads. So 3 of those 4 outcomes have what we hope for, which is at least 3 heads coming up throughout the tosses. And so our answer to the question would be 3/4 or 0.75. Yes, we have formulas for how to deal with conditional probability, but sometimes it's easier to simply look at the sample provided by our set notation and the sample space. Second problem. Oh, we have new neighbors moving in next door. We meet one of their 3 children. Her name is Mary. We want the probability that the family has at least 2 girls, knowing what we know. So we want the probability of at least 2 girls, given that we know that there is at least 1 girl, Mary. So again, while we have formulas for conditional probability, those are more suited to when we have specific numbers provided in the problem. In this scenario, it's going to be easier for us to look at the sample space. The sample space, again, is only going to be divided by the outcomes that have at least 1 girl of the 3. So, we could have boy, boy, boy. Actually, that doesn't work because we need 1 girl, so we can scratch it. We could have boy, boy, girl, boy, girl, boy, boy, girl, girl. We could have girl, 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 boy, girl, boy, girl, and girl, boy, boy. Those are the extent of the outcomes. Ignore the one. Those are the outcomes. Ignore the one that doesn't fit the problem. We want at least 1 girl because we know that they have Mary as a child. So there are a total of 1, 2, 3, 4, 5, 6, 7 outcomes that make sense since we know there's at least 1 girl. And what we want is the outcomes that have at least 2 girls. So there's 1, 2, 3, 4, 5 such outcomes where there are at least, oh no, actually that last one doesn't have 2 girls. So there are only 4 such outcomes that have at least 2 girls. 2 girls, 3 girls, 2 girls, 2 girls. That would be it, so our outcome would be 4/7. Now in this case, if we wanted it as a decimal, we could write 4/7 as a decimal. Please correctly round it to 3 decimal places of 0.571. In problems, I will be clear as to whether I want a simplified fraction or the decimal rounded accordingly. One more problem, and that problem is now on the screen. We're tossing a coin and rolling a die. We want the probability of having a tails or an odd number, given that the die did not land on 1. So probability of tails or odd, given that it was not a 1. Now, yes, we could use formulas to do this, but it's just going to be easier, again, to consider the sample space. So we're tossing a coin, rolling a die. We could have a heads with a 1, heads with a 2, heads with a 3, heads with a 4, heads with a 5, heads with a 6, or tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. However, we know that the die did not land on a 1. So ignore the results where it did land on a 1. They don't matter. We know they did not happen. We know they're not going to happen. So how many total outcomes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many of them have what we wish to have happen? In other words, either a tails or an odd. Well, all the tails would be okay. And then we have 2 over here that would also work. So we have 1, 2, 3, 4, 5, 6, 7 all told that work. 7 out of 10 is 0.7. If it comes out spot on like that, we can write it in that form. And there we go. 7 tenths or 0.7. So with conditional probability, if we have given you individual probabilities as decimals in the problem, then our formula is likely the easier place to look. However, if not, probably viewing the sample space and looking at it through this method, which really and truly is the same as our formula if we wanted to argue it through, this would also work, and sometimes it's just easier to look at things this way.